Well, what I'm going to talk is exactly about extraordinary optical transmission and some of applications. And the outline of my talk is, first of all, to give an introduction about what it means, extraordinary optical transmissions. Then I will talk about surface plasmon polaritrons. And then I will describe the phenomena in corrugated metallic films. And after that, I will explain for the theoretical formalism we use to study the structures. And finally, I will give you some examples of these applications, which they can have some potential applications and still in the interest of the scientific community. Well, what means extraordinary optical transmissions? The transmission through holes, drills on metallic and opaque screens was studied from ancient times, even from the development of the obscure camera in the middle of Renaissance time. It means extraordinary optical transmissions. From the study of light passing through small holes, we know that if the hole is greater than the wavelength, almost all the light passes through easily. But if the hole is smaller than the wavelength, only a small amount of light passes through. Well, so this is the Villate article from 1944, in which he demonstrated that light passing through a small hole, circular hole, drilled on really thin metal film, is proportional to E over lambda to the 4. So it means that for holes with smaller than wavelength, the transmission decay is going to 0. So we expected that no light passed through small holes. Well, in 1998, Everson, in a really milestone experiment, demonstrated that the light passing through a whole array. This is a whole array drilled on a metallic film, and he found that the transmission was really higher than expected from the Villate theory. So, if we define the transmission as the transmitted power over the power directly impinging on the hole, define this, the transmittance, the Villate theory predicts that for a subwavelength hole, the transmission is of the order 10 to minus 3. However, in the experiment of Everson, he found that the transmission is greater than 2. It means that the light impinging on the light directly on the hole is a half than the light that finally passed through the holes. So it means that in this opaque thin film acts like it's not only a passive barrier but also is an active one. So the explanation about this phenomena, why the transmission is higher, took some time. But from the beginning, the theory of Everson was thinking about of the surface plasmon as responsible for this phenomena. So, so it means that extraordinary optical transmissions opens a new and actually still open a field of research. Well, what is surface plasmon polaritons, and what is its role in the extraordinary optical transmission? Surface plasmon polaritons, as in the previous talk, he defined the plasmon as a quantization of the oscillation of plasma of free electrons in a metal. So we have here a metal, and we have a dielectric. So a surface plasmon polariton can be viewed as the excitation of a coupled state between the light, the incident light, and the plasmons inside the surface of a metal. How can describe easily? Surface plasmon polariton is just a superficial wave propagating along the interface between a dielectric and a metal. This wave is evanescent in both mediums, so it decays, and well, this is the relation dispersion for surface plasmon polaritons. So what we see, this is the light cone. So this is the dispersion curve, and is below the light cone. So what we see is for this region, it's impossible that the light, the incident light, can excite surface plasmon polaritons. So how is the way to excite this? What we see is we modify the structure, and if we modify the structure, then the dispersion of light can occasionally, here the conservation of energy is maintained, but the problem of the coupling of the light with the surface plasmon polaritons is a problem with momentum, the momentum of light. So in this case, the component parallel to the surface in some moment can obtain an additional moment that allows the coupling of light and the surface modes. So this is the K incident, is here in this region, and this is the G, this is the additional momentum provided by the structure, and sometimes the lattice reciprocal momentum. So if we imagine as a block structure, so this can give an additional momentum that allows the coupling between light and surface modes. So by structuring, what's the mechanism of surface of the extraordinary optical transmission? So for that, we have a metallic film with substrate and superstrate. So we need surface modes in both surface, coupled through the hole, the drill hole in the metal field. But these weakly coupled surface modes also are coupled to the continuum, this is the radiative modes. So this is the first thing we need to have extraordinary optical transmission. A second one is also a subwavelength hole, isolated, can support localized electromagnetic modes that enhance transmission. It's also a fundamental fact is that the field, the electric field, is enhanced in the surface of the metal when there is a coupling with the incident light. Another thing, important thing for applications is also that the transmission in a Holy field can be affected by the presence of molecules, nearby molecules. So it can be a useful detection of some materials, biological molecules, or even explosives. Well, so now I will describe the basics of my work is the extraordinary transmissions in a simple structure that is described here. We have, this is the metallic film, superstrate, substrate. Here there is a slit drill on the metallic film. This is the image of the structure. And surrounding the slit, there is a groove array. This groove array, so this structure also shows extraordinary optical transmission, not only two-dimensional periodic nanostructures can show that. This simple structure, one periodic in one dimension, can also have this. So what are the mechanisms? Which are the mechanisms that describe the optical transmission in this system? So we have here this this graph. Here is wavelength, depth of groups, the depth of groups, and we have two mechanisms. Also, we observe here and here there are regions of high intensity. This region of high intensity is due to the Fabry-Perot modes inside the slit. It's the first thing we need, that the slit represents as Fabry-Perot modes. Also, we have here the white points. The white points represent the electromagnetic modes on the surface. These were calculated by an infinite array of grooves with this geometry, and this is our points of resonances of the surface. Well, now, as we can see, there is a point here, this region, where the intensity of the transmission is very high. Why? So we have there is a coincidence of the surface mode excitations, the Fabry-Perot modes also, but here also it corresponds to some fixed depth of the grooves. So what we have here is inside the groove there is a cavity mode, excitation of cavity mode, but this cavity mode also emits radiation, and the emission and the interplay between the emission between grooves and the slit and the cavity modes can enhance the transmission. So this value is around 15. This is the normalized transmission. But we have an additional mechanism to increase the transmission through the structure. Is by molding the period of the array. So if you have, for these values, taking this in this region for 850 nanometers wavelength and almost 175 nanometers in the groove depth, and adjusting the periodicity to this range, we can obtain even a transmission about 150. It means that 150 of the light, the enhancement of light impinging directly on the slit is enhanced by a factor of 150. Well, this is, quickly I will describe the coupling mode method, was a semi-analytic method, which solve consistently the Maxwell equations in 3 regions. So we divide in 3 regions, so we expand adequately in this, here there is a field, electromagnetic, the electric field. We expand this way in plane waves. Here in this region, the region 2, so we have the slit, we have the grooves. The grooves can also, even the formalism allows that this region corresponds, or the electric constant of this region is E1, here E2, here E3, and we have also the metal. Well, the formalism is is an appropriate expansion in each region. So here we have cavity modes to expand the fields, and here we have only the transmission, but we have reflection. This is the incident electromagnetic field. This is a factor for the reflection here. Here we have also incidence, reflection, transmission, and finally we have the transmission here. So we solve these equations to find the power transmitted, the eta, this factor, and also this factor is that this is normalized to the power incident on the whole, and this is normalized to the power incident on the system. Well, we match the equations in each interface and solve, and finally we obtain these equations. So each term is described in this figure. So we have the illumination. This is the incident intensity of light. So we have this interplay between the fields, the E beta, E alpha, are the intensity of the fields in the effects, the slit, the groove, and we have this term, interplay. This term is given by this green function that relates these two fields. And we have also this G alpha, which relates the intensity of the field in incident field and the field after the slit. Well, so the illumination is defined in these terms. So we solve these equations and we can find the transmittance. Well, so the motivation for the optimization of these structures is based on this article. So what we have is here is the nanostructure. This is the type of known as bullseye structure. It's just a circular hole, and it has some trenches, circular trenches around the circular hole. And it can, the structure behaves as like a nano antenna, and this nano antenna collects light and is squeezed through the hole. So here is the nano antenna, but here there is a detector. So what we expect is that this region is of the subwavelength dimension. So in the development of sensing, it could be very important, because when here could be is semiconductor, the semiconductor of the detector, and it can reduce the signal noise radio, and also increase the speed of the detector. So we have a system mix. So we have a nano antenna and we have a detector. This is the structure described before. We did it for the infrared regime. So we have the slit, the grooves, and the parameters. And we developed an algorithm of optimization. What we expect is have the higher response of the system. So as we mentioned, we need first to have a resonance of type, of fabric period type inside the slit, is the first thing. Then we also need cavity modes inside the grooves, and then we can modulate the interplay between the grooves and slit. And finally, we obtain an optimal structure. This optimal structure, to increase the optimization, we use a gradient conjugate maximization code that allows to to have non-periodic or non-homogeneous structure. So this is what we obtained. This was for 1.35 nanometers wavelength. So first of all, we find this is the fabric period modes. Then, when we have the fabric period mode, so we have the transmittance as a function of the periodicity, and for different group depths. So we are optimizing two parameters here. Then another thing which is very important is the distance between the slit and the first groove, and the nearest groove. So we also optimize that. And then we also have here the profiles. We have the which is the best resonances parameters. And then we use the conjugate gradient method for non-uniform. What does it mean, not uniform system of structures? It means that here, for example, not all the distances are not the same, or the width, depths, or even all grooves can be different. So we use this. It's a very expensive in time calculation. This one, it took almost 3 months of calculations, but what we obtain is that the best structure is this one. This one is, if you increase the depth of the grooves, this is the slit, so we can obtain a best result, almost comparable with the non-uniform, when all the grooves are different. Well, it means that by increasing the depth, the scattering cross-section could increase and compensate the distance to the center. This is some kind of results. You can check in this one. If you are interested in design some of these structures, you can check it in this publication. Well, another thing is, I will describe quickly is this is another option for a detector. This is an array of lenses, and here is the detector, the pixel detector. So what we do is just put a flat lens here and illuminate our structure with this lens and calculate also the transmission. We develop, we calculate the fields, the electric fields. We use the paraxial approximation, and then we obtain the focusing. So the first thing was to describe the light beam, and then change the term of illumination in our equations and obtain the transmittance. What we obtain is, using a lens, this transmittance is normalized to the total energy who's impinging the system. So what we obtain is almost the 80% of the incident light passing through the slit. This expected result is very simple, but what means is like the lens, what is doing is increasing the scattering, the cross-section of the structure. So in this factor of here, we also, what we use after that is use not only the first system is only a single slit. You use it the same for a slit and groove array, but the results are not similar. You increase only 5% with the slit groove array. So it means that the light is so concentrated by the lens that there is no need of to have the groove array. Sorry. The results. So this is with single slit. It's a black curve. The red cube is only one slit, one groove in each side of the slit, and with 2 grooves. So we see that the increasing is almost nothing compared with the single slit. Here we have this graph in terms of the number of grooves, and we can obtain 5% with 4 grooves, but then it remains constant, the transmission. Well, this is another results. Also, you can check if you are interested in this structure. And well, the next step is about photon sorting. What means photon sorting is just we need that our system can resolve different wavelengths. So we have these 3 structures, different structures, bullseye. This is an article from Evesen also. So we have the parameters of this structure is different from this, so that each structure is resonant to a different wavelength. So in this circular hole, we'll pass only one wavelength, here another one, and here another one. So we have differentiation by color. So if this is incoming light, and these detectors will detect a different wavelength. So it is also done with slits and grooves, linear grooves. And this is our system. We studied this system. So we have this. This one is optimized for 1.35 microns, and this is 1.5 microns. So the parameters of these two pixels are different. And what we show first is that effectively it has resonances in 1.5 and it has resonance in 1.4. So as a demonstration of principle, it works. So it's simple. But we also study, here we can differentiate transmission per slit, and but also we study the dependence of the region, because here we are 2 pixels totally separated. In the resolution of the colors, it's important also the distance between the holes, because it can be used for high in cameras of high definition. So we need the pixel as smaller as possible. So this one, we have 2 pixels separated, but we can see the transmission. This is for 1.35 microns. So we have to study this complex structure. We use these models, only 2 slits, a pixel and a slit, and the double pixel. The parameters in both are different, and we have 3 regions, so we can see how it start to disappear. This is for the double pixel, so this is homogeneous. And here we can see the transmission. We obtain the same for 1.5 microns, so we have regions where where the slits are very close, but still we can resolve 2 different wavelengths. Well, this is another conclusions. And finally, this is work. This is the use how a single hole can be used to detect magnetic field. So the motivation of this work comes from this paper from Professor Kim. So what we have here is incident electromagnetic field, but this geometry, what we can have is that at the entrance of the hole, this is a metallic film, this is a hole. At the entrance of the hole, the magnetic field and the electric field parallel to the surface are not perpendicular. They can have different angles. And what we see in the distribution of the fields is that this is the electric field, the red is the magnetic field, so we see that the distribution of the electric field on the surface is the response is dependent of the direction of the magnetic field. So this is what we have. We construct some similar, but we use 2 beams, and these 2 beams, one is perpendicular to the surface, to the hole, and another one is grazing the surface, and we can modulate the angle that the electromagnetic field, the electric field and the magnetic field at the entrance of the hole. We can modulate, vary the angle, and we obtain the same result based on our equations. So we show that the response, so you see the electric field is along the x-axis. The magnetic field we can direct along any angle, and the distribution of the fields is dependent of this angle. Well, so what we need to use the magnetic field for detecting the isolated hole for detecting magnetic field. We need this mechanism, so we need the excitation of modes inside the hole to have resonance and transmission, we have calculated also the angular dispersion of the radiated fields, but fundamentally, the main result is that the circular hole is of dipolar magnetic nature. Well, this work is for a rectangular hole. So in a rectangular hole, we can show that the transmittance is dependent of the aspect radio. Here, the rectangular hole presents a resonance close to the cutoff wavelength. It is given for this, and it was in this paper showed that the transmittance is given for this expression. So if we replace this term here, we can show that the resonance crest increase when the aspect radio increase. It means aspect radio is the radio between this length and this dimension. So what we do is the same as in the circular hole, two beams, and we control the direction of the electric and magnetic field inside the entrance of the hole, and we have these configurations. So we have this one, electric field and magnetic field perpendicular, magnetic field and electric field. What we wanted to show is the sensitivity of this structure to the direction of the magnetic field. So what we found is the maximum transmittance as we obtain is when the electric field, when the magnetic field is directed along the long side of the rectangle. And we show that effectively the intensity of light is proportionally to the magnetic field. So the magnetic field determines the transmittance through the rectangular hole. Well, this is I should acknowledge to the Proyecto Plaisir, the University of Zaragoza, and the Instituto de Ciencia de Materiales de Aragón when I developed my doctoral thesis. Thank you for your attention, and any question?
Thank you very much, Fernando, for this interesting talk. We have time for short questions, 2 or 3 questions.
I have 2 questions actually. I worry about the impurity and defects in the samples because I didn't listen anything about this kind of things that are actually in the real samples. And the dimension of the cavities are in the range of the micrometers, right?
Yeah.
But some defects of some impurities are in the same range. So why don't you consider this kind of things in your calculus?
Well, this is a theoretical result. So we were collaborating with some experimental groups, but we really didn't obtain, I would say, consistent results. So that's why we don't care. We started some work about the influence of some molecules near the hole, but we really we didn't have time to finish it. But it's absolutely ideal systems. So but in the future, I expect to work on that.
More questions? More questions? Fernando, are you working now in these approaches here in the university, in University Central, or is just your past work, or what are you talking about now? Are you working now?
Yeah, the university, I live for a while this work, but I'm starting to recover the last part, the response of magnetic isolated holes, and we are in the university. We are developing also a project in quantum plasmonics, but it's just the beginning. So we don't have exactly, we want to study this kind of structure from the view of quantum plasmonic, but it's just the beginning.
It's very difficult to have there some computational stuff, or how is recorded in there? What is the opportunities for the students?
Okay, well, in Colombia, simulation is simpler because the funding is, we know that the funding here is really, I know, it's very low. So it's difficult to find funding. And I think that one possibility is simulation. And one thing is this, apart from the conjugate gradient method, this theoretical framework is, the solution is really not consuming time of computing. So it's quite quickly. Yeah, it's quick. So it's easy. I can calculate this in my laptop because they are semi-analytical equations. So the numerical support don't need so high.
So let's thank you have a question.
Thank you, Fernando, for this very nice talk. I would like you to elaborate a little bit more about the applications of this work. Could you please?
Well, the applications are still in development, no? Because the motivation is sensing, is the first thing. So actually, there are developments in sensing, as I mentioned, explosives, so even venoms or specific molecules. So it's one of the main topics which is related with these structures. Another thing, important thing, is the color filter or the color sorting, because it can be used easily in cameras or high definition devices. This is another thing. Is also inside a hole, it can be possible also produce second harmonics, and these second harmonics are nonlinear. And this structure can also have nonlinear behavior. So it's also a fruitful area of research. Hyperlensing. With an array of periodic slits, we can construct a superlensing, which is another motivation of extraordinary optical transmission, is to surpass the diffraction limit problem. So we can have a structure, a nanostructure can surpass this one. So this is another application I can, but there are a lot. I have some reviews if someone are interested, because this is a still topic of investigation, active still topic. Thanks.